Inside pretty much everything we rely on, your phone, your laptop, the massive servers that are powering all this AI, there's this whole universe of complexity. And it all boils down to a technology that is so ridiculously precise, it honestly feels like it's from the future. And it's all made possible by one single $200 million machine.
So if you could somehow shrink down and walk around inside a modern microchip, you'd find tens of billions of these little tiny switches called transistors. It's a number that's kind of hard to even wrap your head around. And the features on them are just unbelievably small. We're talking about 10 nanometers. To put that in perspective, that's literally the width of about 45 silicon atoms, just lined up in a row.
Right. So that begs the huge question. How on earth do you reliably build something with billions of parts, where every single part is only a few dozen atoms wide? Well, the answer is this wild process that's part photocopier, part art project, and believe it or not, part controlled explosion. The official name for it, photolithography.
All right, so here's how we're going to tackle this. First, we'll start big, looking at what's actually on a chip. Then, we're going to zoom all the way down to the atomic level to see how it's made. And finally, we'll pull all the way back out to understand why this is, no joke, one of the most important technologies on the entire planet.
So, first things first, let's just try to grasp the mind-bending scale we're even dealing with here. The sheer density of information that gets etched onto these little silicon chips is, well, it's staggering.
Here's a really great way to think about it. Imagine trying to print the entire English Wikipedia, all 7 Harry Potter books, and literally every book in your local public library, and cramming it all onto a surface the size of a single GPU chip. Every single letter would be drawn with lines just 13 nanometers wide. That is the level of detail we're talking about. And this machine, it can copy that whole library's worth of information in less than a second.
Okay, so how is that even possible? Well, the best way to picture it is like using a stencil and some spray paint, but on a scale that's almost impossibly small. What you're really doing is building a three-dimensional city of transistors, one floor or one layer at a time. The whole process is basically one big loop. First, you take a silicon wafer and you coat it with this light-sensitive stuff. Then you expose it to light, which basically copies a pattern onto it. The parts that got hit with light get washed away, leaving you with a perfect stencil. From there, new materials are spray painted on, either by etching away material or depositing new stuff. And here's the crucial part. This loop gets repeated about 80 times over 4 months to build up all the incredibly complex layers of a modern chip.
But here's the catch, right? To create those tiny 10 nanometer features, you can't just use any old light. It would be like trying to draw a microscopic detail with a big, thick magic marker. The lines would just get blurry and bleed into each other. No, you need an incredibly fine-tipped pen. And in this case, our pen is a very, very special kind of light.
So that fine-tipped pen we need is light with a wavelength on the same tiny scale. If you want to draw lines that are 10 nanometers wide, you need something like 13 nanometer extreme ultraviolet light, or EUV for short. The problem, this kind of light doesn't naturally exist here on Earth, so you have to make it from scratch.
And the process for making it is it's completely wild. Inside the machine, a microscopic droplet of molten tin is fired out at over 200 miles an hour. A laser zaps it to flatten it into a perfect little pancake. Then, a second, immensely powerful laser, we're talking 10 times stronger than a laser that can cut through steel, blasts that tin pancake, vaporizing it into a super hot, glowing plasma. And it's that glowing plasma that finally gives off the precious UV light we need.
Just stop and think about the precision here. You're hitting a microscopic target that's moving at insane speeds with 2 perfectly timed lasers. Now imagine doing that 50,000 times every single second. That is the actual heartbeat of this machine.
But, creating the light is only half the battle. EUV light gets absorbed by almost everything, including air and normal glass lenses. So the entire process has to happen inside a perfect vacuum, using a whole series of incredibly complex mirrors instead of lenses. But even these mirrors, which are themselves masterpieces of engineering, absorb 30% of the light that hits them. So after bouncing off more than 10 of them, less than 10% of that original hard-won light actually makes it to the silicon wafer.
Okay, so with that incredible light source at its core, let's zoom back out to the factory floor, or what they call a fab. This whole thing is like a perfectly choreographed, completely automated ballet. Wafers just glide from machine to machine in this multi-billion-dollar dance of pure precision. The whole place is a clean room, so sterile the air has fewer particles in it than a hospital operating room.
The whole guiding philosophy behind this operation can be summed up by a Dutch phrase from the company that builds these machines. Meten is weten, which means to measure is to know. Before a single pattern gets zapped onto the wafer, the machine meticulously maps it out. You have to remember, they're building 80 layers on top of each other. If just one of those layers is misaligned by a couple of nanometers, literally a few atoms, the connections won't line up and poof. Every single chip on that multi-thousand-dollar wafer is completely ruined.
And you know, these $200 million EUV machines don't actually do the whole job alone. They're part of a bigger ecosystem. A good way to think of a chip is like a skyscraper. The transistors are the foundation, they're tiny, they're complex, and they are absolutely critical. But the wiring that connects everything on the upper floors is much larger. So the fabs use these super expensive EUV machines for that critical foundation, but for the bigger wiring layers on top, they use older, more cost-effective machines. It's really an economic decision. You use your most advanced tool only where you absolutely have to.
Okay, so we've gone from the scale of individual atoms all the way up to a billion-dollar factory floor. Now let's bring it all together and talk about why this incredible feat of engineering really matters to every single one of us.
And this technology is definitely not standing still. The next generation of these machines, they're called high-NA EUV, basically use even larger mirrors to capture light at wider angles. It's like getting a better lens for your camera. This is going to let them shrink the features down from around 13 nanometers all the way to just 8. And that leap means even more powerful, more efficient chips for everything from AI to medicine and beyond.
So look, if you take away anything from this, let it be this. Our entire digital world is built by photocopying patterns with a special kind of light that's created by vaporizing tiny drops of tin 50,000 times a second. It's this delicate dance of stenciling and spraying, repeated over and over again, where an error the width of a few atoms means total failure. This technology is, without a doubt, the absolute bedrock of all modern computing.
We've seen how this tech enables the world that we live in right now. But the next generation is going to print features that are just 8 nanometers wide. We're talking about the width of maybe 30 atoms. It really makes you wonder, right? As we keep getting better and better at manipulating matter at the atomic scale, what completely new technologies, what currently unimaginable tools will that unlock for our future?